right, so who does more work? Raise your hand. Think you know. Sergio, thanks for raising your hand. You think the running one does more work? Why?
Because he has a greater velocity.
He has a greater velocity. Okay. All right. So, Kevin.
I say they have equal work.
Equal work. Why equal work?
Because they're both going to the same spot.
They're both going to the same spot. Okay. Kim. Equal why? The distance the place they start and it's the same? He's on this side, on the left side. Okay.
Yeah, one of them does it
All right.
farther down.
Alright, that was just because I'm a terrible artist.
Okay.
Okay, anyone else? Maria, you had something. Who'd you say? I heard you talk about. Who'd you say?
I kind of confused because in that first, I don't know.
Okay, Maria was saying the person who's walking does more work because they take longer.
Yeah, but I don't know.
Right? So we have Sergio who says they do more work. The runner does more work because he's going faster. Maria says the walker does more work because they're taking longer. And Kim and Kevin say that they do the same amount because they start at the same spot and they end at the same spot.
Yeah,
So who's right?
Same with Kevin.
Sergio.
You can make valid arguments for all of them, right? If this is hour, if they get paid by the hour to climb this hill, who's going to make more money? The walker will make more money, right? So aren't they doing more work? They're making more money, right?
yeah.
Sergio, don't put that in your ear. Hey, don't put that in your ear. We're teaching right now. Come on now. Okay. So, who does more work?
They do the exact same because
Double.
What force are they both working against?
gravity.
Gravity. They have the same mass, right?
But,
So, their force of gravity is the same. Thank you, Nike. Their force of gravity is the same. Right? Upward force, 75 times 9.8. Right? Distance. How far do they go parallel to that force? 5 meters. Okay? So they do the same amount of work because they have the same force over the same distance. Does that make sense? Someone might say, well, the guy who's running is sweating, the person who's walking isn't, so the person who's running has to do more work. They're sweating. They're burning more calories, right?
Mhm.
Well, the work your body does is different than the work that you do in the physical. Does that make sense, guys? All right. So according to the work equation, they do the same amount of work because they ascend the same distance using the same force. So what's different about the situation? What is different between the two paths? Well, maybe instead of paths, what's different about the ways they climb the hill? One climbs faster. Right.
That runner does the work in the short amount of time than the walker.
Perfect. The runner does the work in a short amount of time than the walker, right? Okay. Now, instead of talking about runners and walkers, let's talk about steam engines and horses. Okay? Because way back in the Industrial Revolution, we were trying to replace horses with steam engines. So what was the argument that one would make about a steam engine versus a horse?
It's more efficient. You don't have to feed it water. You have to feed it coal. Or not feed it, but you have to give it a source.
So you argued and refuted your own argument right there.
No, but then
You said we don't have to feed it, but we have to give it fuel, right?
yeah.
Okay, so they're not going to make that argument, right?
And then does the steam engine go faster?
Okay, so that's the argument they might make, right?
Or it holds more.
The steam engine can do more work in less time than the horse, right? That's the argument James Watt made when he was trying to sell Ireland on a steam engine. Okay? And that's where the whole idea of power came from. Okay? Horsepower comes from that.
Isn't that
Right.
like watts and stuff?
Yep, it is watts.
Like, isn't it like 746 watts equals 1 horsepower?
How'd you remember that, but you didn't remember this?
That's my understanding.
That's less interesting? Okay. So, power.
I like horses.
Okay. Power is a quantity defined as the work done per unit time, or the rate at which an external force changes the energy of an object. So power is the work done per unit time. And also think about this. The rate at which an external force changes the energy of a system.
No.
So, based on our definition of power, what's the difference between these two students? The time, right? So who's more powerful? The sprinter, good. The person who ran. The person who ran is more powerful, right? Because they took less time. And those who are thinking about this mathematically, you know the word per means a ratio, means division. Good. So whenever we're talking about, when we use the word per, that means divide. When we use product, that means multiply. Per means divide, right? So then we get an equation here that says power equals work over time. Does that make sense? Yep.
Do we answer the second question?
Yeah, what's the difference about the pass? What's the difference? The runner had more. The runner had more power. Okay? The runner had more power. Alright? Does that make sense, guys? Okay. Now the units on power is named after one of the inventors this team mentioned. Watt.
Watson, is that his name?
Nope, his last name was Watt. Okay. Not Watts like the football player, just Watt.
Benjamin.
Okay. So Watt is the units. Alright? Now, guys, stop. Kevin, Moses, stop talking, please. Okay. What's the units on work? Joules. What's the unit on time? Seconds. So 1 watt, and usually to denote between work and watts, I put little hats on my W. Okay? Because this W is work, this W is watts. Okay? It can be confusing. Alright? If you use the same W, it can get confusing. So, 1 watt
That's not a good hat.
is 1 joule per second. So that is what 1 watt equals. Does that make sense?
Yes.
Now I'm going to take this equation just a little further. Power equals force times displacement over time, right? What's displacement over time? What's displacement over time? Velocity, good. So that means that power also equals force times velocity.
So it doesn't.
The same equation. Okay. All right, does that make sense, guys? So how can we figure out the power here? So we can do mass times gravity times displacement, right? Divided by time, can't we? You won't time it. No, you won't. Okay. The only questions that don't get answered are the ones you don't ask. All right. So let's talk about the problem. Let's say that this person takes 30 seconds to climb the hill. Okay. Let's say this person takes 15 seconds. Okay. Now, in order for the force times velocity equation to work, the force and the velocity have to be in the same direction. Otherwise, you have to do the cosine theta in there as well. So let's talk about this person's vertical velocity. Okay. So they go 5 meters in 15 seconds. So what's their vertical velocity? 5 meters in 15 seconds. What's their vertical velocity? 3. Good. 5 divided 15 equals 3 meters per second. Does that make sense?
Yeah.
We can figure out this person's vertical velocity as well. But I want to use both equations. So we're going to use this one using work and time. And we're going to do the runner using force times velocity. Does that make sense, guys? We could use both equations for both if we want to, but we're on a limited time, and I don't want to run into the last 5 minutes of the hour. All right, so let's try this out. So for the walker, what's their force? For the person walking, what's their force?
Gravity.
Force of gravity, right? So mass times 9.8, right? So force equals 75 times 9.8. What does that equal?
735.
735?
Yeah.
Okay. Newtons, right? What's their distance?
Okay.
5 meters. Or displacement, sorry. So we can figure out the work by doing force times displacement, right? So work equals 735 times 5. 3,675. Oh, that's not watts. We're getting ahead of myself. Almost confused with all. 3,675 joules. Does that make sense, guys? Yeah? So now to find the power, what do I do with that 3,675 joules? Divide by 30. Good. So power equals 3,675 divided by 30. Work divided by time.
132.5.
What's it?
132.5.
132.5 watts. Does that make sense, guys? Any questions?
5 over 15 is 0.3.
What?
Velocity over here
Yeah.
is 0.3.
Oh, 0.3, not 3. Wow. Thank you, Lynn. Okay. Velocity around is 0.3, not 3. Divide the wrong way. I teach math too. All right. So there's the power of the walker, right? Now we said the runner should have more power, right? We could do this same thing, 3,675 and divide by 15, because the time was only 15 and get the same answer, right? But I want to use this equation, right? So for the runner, yep,
Wait, so you said you could just take that and divide by 15?
it's 22.
Yeah.
So 13,022.
No, 122.5.
Yeah.
Ah, 22. Gotcha. Man. Thank you. Okay. So the runner, what's their velocity? 0.3 meters per second, right? What's their force? 75 times 9.8, right? So that equals
7,000, right?
735.
735, right? So now I can find the power by doing force times velocity. $735 times 0.3, what do we get?
230.5.
230.
20.
220 watts. Right? So is the runner more powerful? Yes. Okay. Now, when James Watt was trying to sell his steam engines, he was trying to say these are more powerful than horses. And therein lied a certain conversion, which ended up being kind of arbitrary for how they figured it out. Because it all depends on what kind of horse you use. I mean, you definitely can use a mini horse. A mini horse is going to be a lot less powerful than a Clydesdale, right? So, all depends on what kind of horse you use. I'm sure they used the horse that was the standard horse for farmers in that time. But what's come up with is a horsepower comparison, right? So 1 horsepower, okay, equals 746 watts. Okay. So when you see a engine that has 200 horsepower, that means it does 200 times 746. 200 times 746, what's that?
That's 149,200.
149,200. That means it does 149,200 watts of power. Okay? That's a pretty bright light bulb. You guys probably saying, what? Engines and light bulbs? Because the watts that we're talking about here with people running up hills and the watts that are on the light bulb are the same thing. Because power is all energy added to a system, right? If that energy is added by mechanical forces, like a motor or an engine or someone running, or if that energy is added by a light source, or if that energy is added by a wire, giving power to your phone, okay? It's all the same power. It's all joules per second. Okay? So when I said that motor, that's a 200 horsepower motor, will be a very powerful light bulb because it's all measured the same way. It's all measured in watts. So we can figure out the horsepower rating for a light bulb if we wanted to. Sounds kind of silly, right? But we could. That'd be kind of cool. I'm gonna start reporting all my light bulbs in
I
horsepower.
wonder how it is that they make super strong cars that have like 550 horsepower.
I don't know. If I knew that, I think I would do fixing cars. I'm sure there's some people that could tell you that. I'm not a big car guy, so I don't know. So 1 horsepower, 746 watts. So how many horses? How strong is the walker compared to a horse?
What?
How strong is the walker compared to a horse?
Like half, like not even one leg.
Okay, we can convert this to horsepower by using conversion factors. 122.5 watts times 1 horsepower over 746 watts. So watts cancel, right? How many horses was the walker?
0.16.
0.16 horses. So they are from the knee down to the hoof on one leg.
Yeah.
Okay. Not a very strong route to the horse.
Oh,
Not very powerful.
what is a horsepower?
A horsepower is the power of 1 horse. That's where they came up with it. Because they're trying to sell steam engines versus horses. Okay? So if they had a 2 horsepower engine, that means it does 1,492 watts per second, or joules per second. All right. What about the runner? How many horsepower is the runner? What? So we do this, and we can figure out the horsepower of the runner. What is that?
0.3.
What is it?
0.3.
0.3? Yeah. Now here's the question I have for you guys. Do any of you think you can create a horsepower of power?
Absolutely not. Yeah, we did this in like.
You did it in physical science, but not all in physical science.
But
So-
I bulked up since
Does any one of you think you can do a horsepower power? Now we don't have a 5-meter tall hill, but we do a staircase, right?
then.
Okay. We can run up the stairs, right? So we'll just use approximate weights, approximate masses. And let's see if anybody can do a horsepower power. You want to try? Georgia thinks he can do it? Alright.